All right, it's my pleasure to have Dr. Kevin Booth, a former PhD student in my group and current research engineer, working with us on the SysWS operating system project to talk about Rust today. Kevin actually has been given similar talk for like the past 3 years in all my courses, because all my courses kind of involve Rust at some stage. So Kevin basically has become a veteran of introducing Rust and contrast Rust with C. Please feel free to ask him questions. You know, he's on the channel, on the Slack channels. You could also reach out to him for questions. But I would say use Lab 3, the channel, for questions, and Kevin will be there too. All right, Kevin, it's all yours. Thank you.
Great, thanks, Lynn. Can everybody hear me? Everything's good? Okay. Right, so I've been using Rust for about almost 4 years now. I first discovered it in 2017. So I have a pretty deep background, mostly in the low-level embedded stuff, which is good because that's what you guys are going to be working on too. But then I'm going to just kind of give a brief overview of Rust, kind of highlight some of the issues with C that Rust does a good job of solving. We'll talk about basic syntax and stuff like that. And then, hopefully at the end, there will be time for questions. If not, I can stay for however long to answer whatever questions and maybe do some live coding examples if you guys desire. Up to you. So first, I just want to acknowledge some of this material has been borrowed from other sources. It's mostly my stuff, but I've grabbed things from here and there. All right, so an outline of the talk. Basically, I'm going to first start with C, what's good about it, what's bad, and then what's really bad and dangerous about it. Then we'll move on to an introduction to Rust and then some of its basic syntax and overview of key Rust features, things like ownership, borrowing, lifetimes, which if you've read about Rust, you've probably heard these terms. And then just questions. So first off the bat, what's so bad about C? What needs to change? Why does Rust exist? Before I hate on C too much, let's talk about what's good about it, right? So C has a nice, really straightforward machine model, right? It's pretty simple. It offers the idea of like easy programming, right? What you see is what you get. There's no like weird abstractions or anything beneath the hood that's there to confuse you or cause inefficiency, right? And this is quite important in resource constrained environments, like the microcontroller that you've been working on. Right. So this allows you, as you saw in Lab 2, to directly control, which means communicate with hardware. All right. You can set specific bits of specific ports with ease. Now, if you were trying to do that in JavaScript, you'd have a little bit more difficulty. All right. So overall, C prioritizes performance and efficiency over safety. You do all of the memory management yourself, and there's no sort of like garbage collection or any kind of automated stuff behind the scenes. And in general, this is regarded as desirable for advanced programmers. Now I'm here to question, is it actually really desirable? It's a matter of opinion. So one bad thing about C is it's not strongly typed. It has what's called a weak type system, which you guys are probably familiar with, but it basically means that type errors are pretty easy to make. You can promote and coerce and cast integers freely, same with pointers. There's no real protection between unsigned and signed compatibility. Same with overflow and underflow. Those occur silently, and you won't detect it. And then finally, you can do what's called type reinterpretation, which is just a fancy way of saying arbitrary casting. And you'll see copious usage in most C programs of types like a void pointer or a character pointer, which is just really byte pointers. And these don't really express the actual type of what's being pointed to in a good, strong way. So another major problem with C is that it's really easy to make memory mistakes. You can have simple memory mistakes like a null pointer dereference, right? There's no bounds checking in C, so you get a lot of buffer overflows or out of bound accesses. You could even have errors and bugs that stem from string formatting, which is pretty hilarious. And then, of course, the classic design problem of having null terminated strings. And then we have way more complex or subtle memory mistakes, things like dynamic memory errors due to, potentially like leaks or something when you forget to free something, using something after you do free it, which is also called a dangling pointer, and then double free, right? Freeing something after you've already freed it before. And pretty much every major bug that's reported, all of these vulnerabilities are due to memory mistakes like this. and they frequently cause catastrophic results, huge security problems. So do developers actually make these mistakes? And is it C's fault? Or is it the developer's fault? Well, it's both. But even expert developers do make these kind of mistakes. So here's a classic example. This is a bug from the 2002 version of FreeBSD, which is alternative to the Linux kernel. It's kind of a similar kind of Unix-like operating system. And it was in the function called get peer name, which basically just gives you the host name of the system. All right, it takes that and it copies it into a buffer provided by the user using this copy from kernel function. Right? Now, if we look at the code here, we'll see that copy from kernel takes a maximum length of this user provided buffer, right, which the user should also provide, right? And that's an int type, which in C is a signed integer on pretty much every platform. All right. However, when it actually performs the memory copy from kernel space to user space, it uses mem copy, right, which is this length parameter is an unsigned integer, right? So, you know, they have a lot of checks to make sure that there's no kind of confusion or issues there, but that doesn't prevent sign problems. So what if an adversary, right, a user program that was malicious or just stupid, gave a length of -1 for this buffer size, right? Passed in -1 to this function. What would actually happen is this condition here would be false, right? So we would use the length provided, max length, which is actually -1. However, when you pass in -1 to mem copy, you get the unsigned representation of that, which is basically the largest 32-bit integer possible, right? And then you end up copying basically as much of kernel memory as that exists out to the user buffer. And that's a big problem, right? So just a very innocuous, kind of simple, seeming innocent bug of signed and unsigned inequality there, right? This mismatch causes a huge security problem. So in Rust, this would just be a simple type mismatch. It wouldn't even compile. Of course, there are some good things about C. So let's take a look at what's good. In this, you know, very simple example, we have a basic struct with 2 integers, right? When we allocate space on the heap for a struct like this, right, this is what happens. You have this pointer and on the stack, and it refers to probably in this case 64-bit object on the heap, right? 2 32-bit integers, right? So you're guaranteed a precise memory layout. That's C's guarantee. Very simple machine model, right? Then when we access it, right, we can mutate it, no problem. We can set the value of A, right? Nothing unique there. And we have what's called a lightweight reference, right? This pointer type, very easy to use. There's no other weird semantics. It's just an address. And then we can free it, and everything kind of happens explicitly. We have a very clear destruction action where we're removing this memory on the heap, right? And returning it to the system allocator. So that's great, but it's a little bit simple, right? What if we make this example a little bit more complicated, right? I'm sure you can see where I'm going with this, but let's say that we have another pointer pointed to the same location, and we call it alias because it's an alias. So now we have these 2 pointers pointed to the same heap allocated struct, the dummy struct. And when we free one of them, it actually frees, it removes the entire heap object. All right. So then we're left with a dangling pointer. And if I were to try to access, in this case, read the value of A, there's nothing there. It's going to read perhaps the old value. Somebody may have overwritten it. It's going to be garbaged. It's non-deterministic. We don't know. All right. And then if I try to free it again, it's a double free. And that's also non-deterministic, right? Most systems will catch it. They won't do anything, but it's not defined by the C language standard. All right. So this is a major problem, right? Even a simple basic example like this, you, the programmer, has to be aware of what's going on with memory. So how can we do better? All right. So you may have had experience with other managed languages, which basically their entire goal is to solve this problem. You know, things like Java, Python, C#, right? In these languages, the programmer doesn't directly access or allocate memory, and memory management is done at runtime, typically based on a garbage collector. right? Which pauses the system every X milliseconds, scans to see which references, which heap objects no longer have any references, and then cleans them up. So there's no explicit malloc or free. And in general, because the programmer doesn't mess with that, you have fewer memory corruption and memory mistakes. Right? But it doesn't come for free. Obviously, there's some overhead to track those object references and to actually run the garbage collector. And this isn't good for real-time systems, right? That overhead and then also the unpredictability of when it will run. In some cases, like in Python, you have a limit on true concurrency. You also have a larger code size because you typically need to build along these big old libraries that may include the virtual machine, like in the case of Java, and other runtime layers. And this requires more memory, and also, it's less efficient in terms of CPU utilization, right? So for a systems environment, right, something like the microcontroller that you're working on, those environments have a little bit different requirements, and we call these systems programming, right? So it needs to be fast, minimal runtime overhead. We don't want to have any kind of runtime because we may not have an underlying OS at all. And we want to make sure that we're supporting direct and easy, access to and control over memory, but we want it to be safer than C or just raw assembly, right? Those are kind of the goals, right? So this is where Rust comes in. So does anybody have any questions up to this point? I'm happy to clarify anything or go back over some of the examples. Okay, no worries. So now on to the good part. So basically, Rust has evolved over the years, but this was a screenshot from their website, I think in 2018 or something. So they used to be a very systems-focused programming language, right? And they had three goals: safety, speed, and concurrency, right? So the idea was you get low-level control, but you also have the convenience and safety guarantees of a higher-level managed language, right? In recent years, they've reformatted their website to this kind of pastel color thing. And the idea is just to empower everyone, not just people focused on systems or bare metal or OS environments, to build, quote, reliable and efficient software. So, whatever that means, in this case, it's focused primarily on doing things at compile time, right? Memory safety at compile time, avoiding garbage collections, and having an underlying runtime. So just to give you a little bit of background on what Rust is, the actual language itself kind of spawned from Graydon Hoare, who was a developer at Mozilla. It was kind of his pet project. He worked on it for a couple of years, announced it in 2010, and then it kind of got taken over by a Rust organization within Mozilla, and they released Rust version 1.0 in 2015. That was the first stable version. Since then, their goal is to release another stable version or an edition every 3 years. So there's also a 2018 edition, and sometime later this year, hopefully a 2021 edition. So like I said already, it focuses on memory safety without the hits in performance. I like to think of it as having a lot of good features of C++, but it's done well. So in the case of Rust, safety is opt-out, meaning you have to explicitly say, hey, I want this portion to not be checked for safety, whereas C++ is opt-in, right? It's unsafe by default, and if you want to use safe features, you have to explicitly choose those particular types and functions. Currently, in my opinion, this is my opinion, it's very well equipped to replace C, right? Totally, fully covers all of C's bases, and it covers most of what C++ can do. And I think in a couple of years, it'll be fully complete in terms of all of the feature set. All right. If you don't believe me, you can look at the statistics, right? So Rust has won first place for the, quote, most loved language on Stack Overflow every year since 2016, right? Now, you may disagree in your first 2 or 3 weeks of learning it. It can be hard to get started, but after a while, you really see
there's something called the Stockholm syndrome.
Stockholm syndrome, yeah. I mean, I don't know if that's relevant. Yeah, so Stockholm syndrome is the idea that you empathize with your captors, people who are controlling you, right? Or people who inflict pain upon you. I don't know that Rust is exactly suffering from that. Maybe a little bit, but I think the benefits are clear, such that it's not just this delusion, right? That we all think it's great when it's really not. There are obvious benefits. That, I mean, yeah, that is a funny anecdote. Okay, so
Quick question.
yeah,
When you say
go
like
ahead.
ready to replace C++, does that mean like the STL or like
Yeah, so
um
that's kind of what I was alluding to. So yeah, C++ has this huge templating functionality, right? And there's a lot of things that you can do. Rust has covered most of it, but not everything, right? So for example, things like generic associated types, things like higher ranked types, those aren't quite fully ironed out in Rust, but we're like 95% of the way there. All of like the functional aspect. So anyway, yeah, why do people actually like Rust? I mean, for me, it has a great feature set. One of my favorite things is that you get the high level convenience of a managed language. You get plus that low level flexibility. You can do both functional programming and imperative programming styles. Strongly typed statically at compile time, and it has pretty good type inference. By default, all objects are immutable, which is kind of nice. More on that later. There's this great notion of like ownership of objects, right? Plus a borrow checker to ensure that all of these rules are followed at compile time. And then a reference, right, which is kind of like a pointer, but slightly different, has very explicit lifetime. So you know exactly how long it needs to last, right? And then Rust has this key rule of mutability, XOR aliasing, which I'll talk about later. And that's enforceable at compiler time. It basically says you can either have one mutable reference to something or multiple immutable references to it, but not both. Right? But, you know, of course, there are some downsides. Nothing comes for free. So Rust has a relatively high cognitive cost. So programmers have to think a little bit harder about the rules for accessing and using memory in a safe way. It has a little bit of complexity in its generic type system, which I'm not going to really touch on today, but we can talk about it after. And then the core system of ownership and borrowing and lifetimes to ensure safety is tricky, especially initially, right? So you'll end up fighting with the borrow checker to satisfy its demands, at least up front, quite a bit. But again, this is my opinion, the pros typically outweigh those cons. And kind of the whole mantra of Rust is you'll spend a lot more time to do it right up front, right? Finding with the compiler. But once you get it to compile, you'll have way, way, way fewer bugs at runtime. And that's super nice for embedded systems where you don't really have a clear way to, you know, express errors back to the user and have them handle it. All right, so let's get into the actual heart of the matter, actual Rust syntax, right? So right off the bat, Rust is strongly typed, and that's typing at static time, right? Which means it's typed at compile time, right? It's not dynamically typed. So here's some examples, right? You can declare, you know, a type like this. We use the let keyword, which is sort of like borrowed from functional languages. So you can say something like let x is the variable name, the type comes after the colon, and you can omit it if it's able to be inferred, and it's 5, right? So this is a signed 32-bit integer, and we give it the value 5, and we bind it to the name x, right? You can infer it based on later use. So if you do something like call a function that accepts a 64-bit int, and you pass x into it, it will be treated as a 64-bit int. You can also specify it in the constant as a literal, like this. And then you know we have the I size and U size, which are platform dependent signed or unsigned integers. We also have various types of strings. There are 2 main types in Rust. One is kind of a borrowed reference to a string, like this, right? So it has this borrowed reference type. And then one is a heap allocated string, which you actually own. And then we have characters, which in Rust are not 8-bit or 1-byte C-style characters. They're Unicode characters, so they're 32 bits wide. And then you have the actual byte type, an unsigned 8-bit integer, which you could, you know, use a C-style character in this way, right? B meaning byte. So this is like a byte character. So yeah, that's kind of a basic overview of the various types. There are several other primitive types, but those are the core ones. The point here that I want to emphasize is that all of these primitive numeric types, when you declare them, each one has a very clear specific width and size in bits, right? So that's super nice and convenient. You know, in the case of C, you may not know what size an int is. It could be 16, it could be 32, or even 64 bits, depending on the system. And that's pretty awful, right? The only thing like that in Rust is I size and U size, and they're very clear. All right, so this prevents a whole lot of bugs. It also has a clearly defined Boolean type, which I find very convenient. You can do things like just declare a false one, or you can have, declaration of conditionals in line like this, right? Just like C, nothing super special there. But having this dedicated Boolean is actually really nice, right? So unlike C, where it overloads this integer type, right? Basically where you say 0 is false and anything else is true, we have this clear Boolean type, which again, helps us in the type checker. At compile time, we can avoid type mismatches, right? So there are tons of examples where the lack of a Boolean type has caused so many issues. One, it's open to interpretation. Is 0 false? Is anything below 0 false? It's up to you. It's up to convention, right? So even in other languages, this is a huge problem. One of my favorite glaring examples is in PHP, which has its own set of issues. The string comparison function returns 0, both when it's equal and when it fails. So that's not ideal. So Rust avoids all of this with dedicated strong types. So just to go into a little bit more detail, here's a couple of examples. All right. So in C, you could easily compare unsigned and signed integers, right? But Rust won't let you do that, right? So here's a C example. I have an unsigned integer with this very large value, and then I have this signed integer with a small negative value, right? And if they're equivalent in C, which means they only have the same underlying bitwise representations, we'll print this thing. So when I run it, you do get that they're equivalent, right? That's fine. Maybe you want that behavior, but it's also not super explicit, right? Now in Rust, this results in a compiler error, right? You can't even run the code, right? And that's because a 32-bit unsigned integer and a 32-bit signed integer cannot be directly compared. They're not equivalent. Of course, you can get around this, right? You can just cast it, but you have to explicitly do that. And that's kind of Rust's whole thing. If you want to do something that's a little bit dicey, you better be explicit about it. And it also still needs to follow Rust basic safety rules, right? So here's a similar example. I'm doing it with characters in this case, right? Here I've defined a character to be value 128, right? In C, we don't necessarily know if this is a signed or unsigned character, but by default, it's typically signed on most platforms, right? So here you see these two values, right? You have, this value of the unsigned int, which we've casted from this character, right? It was 128. So what did that mean? Well, we're not sure. But in Rust, it's super clear, right? So we have the same thing, right? An 8-bit signed integer here, and I give it the value 128, right? Which it can express, but it's going to warn you and say, hey, 128 is actually beyond the bounds of a signed 8-bit integer, right? Because the maximum positive value would be 127, right? But it will still let you do it, right? So there's a little bit more checking, but again, this doesn't violate any safety rules. It's just a little bit of extra confidence in what you're doing. So there are a lot of issues with unchecked overflow and underflow and overflow. There are thousands of examples of vulnerabilities related to this. To make a long story short, in C, it's silent. It happens, and that's it, right? So here I've underflowed the value of this unsigned integer, right? It should be actually -1 here, right? And yeah, you can see, it's an unsigned integer. It treats it as -1, but this doesn't make sense, right? 4 minus 3 minus 2 should not be a massive value, right? In Rust, this is caught, and you get a panic at runtime, right? Of course, this has to be caught at runtime, right? There's no way otherwise, but it still checks. So that's super nice. All right, so on to, that should be second. So on to a little bit of additional, maybe more complicated types. We'll start with arrays, right? So in C, arrays may have a length, but they also don't have to, right? But in Rust, the exact size of everything, at least on the stack, needs to be known at compile time, right? So here we have an array. Sorry, let me hide this. Okay. Here we have an array in C on the left, and we're iterating over it. Notice it only has 8 elements, but we're pretending that it has 10. So the last 2 iterations of this loop may print total garbage, right? We don't know. The point is the compiler is not going to check it, right? Here, the compiler could check this, though more likely if this was a vector or something, it's going to check it at runtime. And what's going to happen is when you try to access something out of bounds, right? The 9th iteration of this loop, if you try to access index 8, you'll get a panic, right? So bounds checking is inherent in Rust, right? And that's done with this index operator, right? Just like C. Nothing too abnormal there, I think. So that's also really nice, preventing out of bounds access, which is also a major source of security vulnerabilities. Okay, any questions so far?
Yes.
Sure, okay.
Back
Will,
on
all right,
back on the slide with the type inference, you said that it's inferred by later use.
Yeah.
Does that mean it's the first later use? Like imaginably you could maybe use X as a 16-bit integer, and then you want to use X again later, and where it's meant to be interpreted as a 32-bit integer. I don't imagine it would let you change the type.
No,
Go
so
ahead.
such a program wouldn't even compile. If you had the same variable being passed into a function that took a 16-bit integer and then a 32-bit integer, that if you use the same variable like X, even if you didn't define the type, it wouldn't compile. The Rust compiler needs to give each individual type, each individual object, a very specific concrete type at compile time, right? So that's what we mean by strong typing. And that's also what we mean by static typing, right? It has to be known at compile time. So if you had something like, yeah, let X equals 5, the compiler will resolve it to either a 16-bit or a 32-bit integer, right? But not both. So that example wouldn't even build, right? So the inference is gonna, it's still like, it would be the same as if you annotated it with, you know, U16 or U32 type def here, but it's not required, right? So in a lot of cases, it's really easy to infer what the type is, so the compiler can do it, right? If it can't, it'll throw an error and it'll ask you to specifically enumerate what type it should be.
Okay, thanks.
Is that clear? Okay.
Yeah, thanks.
Yeah, you can experiment with that on like the Rust playground. It's super easy to play with that. But yeah, type inference isn't changing the type. It's just saving the programmer the hassle of typing the actual type term itself. Okay. So another question? Yeah, go ahead.
Yeah, about typing as well. I guess like in a language like C, there's a notion of a primitive versus a non-primitive type.
Yeah.
In Rust, is everything pretty much non-primitive?
No. There are definitely primitive types, right? So all of the integer types, the basic float types, bool, character, those are all primitive types. There's also things like slices, which is basically a reference to an array, arrays themselves, right? And then everything else is pretty much not primitive, right? So this heap allocated string is not primitive. Box, which is like a heap allocated object, also not, well, that's sort of primitive. It's a debate. But yeah, there is a notion of primitive types versus not.
Okay, and I guess like just a question about strings. Are they null terminated or are they not?
No, right. So that's a huge problem with C and similar languages. No, strings are effectively just, in this case, a vector, right? Or you can think of it as a heap allocated array of characters, right? The first item, it's a struct, right? The first item is the length, and then the second item of the struct is an array, right? Basically a pointer, right, or the hood to a set of characters.
Okay.
Yeah, great question. Okay, so we were, okay, right. So that's arrays. Right, so, okay. I wanted to emphasize that bounds checking occurs, right? There's no way to get around it, short of using unsafe code, but there's no way to get around it. But it's also a little bit expensive, right? So if you were to do this, right here, this, every single time we use this index operator, it's basically going to say, is the index less than the size of this array, right? Which is known at compile time, which is known within the array type, right? Or the vector or the string type, whatever it is. And that, that's just one extra conditional on every axis. So that, there's some overhead, but there are ways to avoid this, right? So in Rust, we typically use iterators, right? So if you're familiar with C++, they also have iterators. Most languages have iterators. And in this case, I've shown it with a vector, but it works with arrays too. You basically use this for keyword, or you can use a variety of other types of iterator syntax to iterate over each element in something, right? And then this doesn't need a balance check to be performed, right? Because it knows the size and it basically just gives you the next item each time. So this is kind of syntactic sugar for iterating over each item in this particular collection, which is a vector, and then printing it. Right. So again, this is different than using this primitive style iteration over the indices of this array and then indexing each one. So this is faster than this. Okay. Oh, any questions here?
What is vecbang doing?
Yeah, that's just a macro to create a vector. I could have just done it with an array. You don't even need that, but it's just another way to create a vector. A vector is a heap allocated array. That's the only difference. Okay. So yeah, some other basics of Rust. One of the things I really like is it nicely blends functional and imperative styles, right? So here's an example of a basic struct, right? Just a circle. You can define the members, the fields of the struct, right? Just like that. You can also have visibility modifiers like public on each one of these fields or the struct itself to allow other modules to use it. There's also a notion of traits. I'm not going to really dig into this, but a trait is kind of like an interface in Java. It's the avenue for polymorphism in Rust, right? And basically you're able to define kind of a function signature, right? A prototype for this method here, area, right? And then any type, any struct which wants to implement this trait can do so like this, right? And it's pretty simple, right? Obviously, pi r squared is the formula for a circle, so you do something like that, right? Another thing I want to mention is in Rust, the methods, the functions have expression-like syntax. So the last line of a Rust function is the return value. You don't have to explicitly say return this value, right? And that kind of integrates with its larger syntax of everything being sort of a blend of functional and imperative, right? So the last statement of any kind of bracket, curly bracketed scoped block will be returned to the outer scope, right? So yeah, so that's kind of the basics of structs and implementing a method, right? Any questions here?
This polymorphized method area takes presumably that's a reference, I guess, to an object.
Yeah. So you would call this if you would say let C equals circle, and then you'd specify the fields, and then you'd say C dot area.
Okay, so that, despite the fact that that function is defined outside of the context of, or maybe not defined, but its references made outside of the context of the circle type, the self parameter doesn't have a defined type until it's implemented with circle or square or whatever.
It does have a defined type, right? And the defined type is based on this,
Okay.
right? Because you're implementing this trait for a particular type. You can't just say implement trait, right?
Yeah.
Because then it doesn't know how to connect it to some actual type, right?
Yeah.
Yeah. So it's a little bit different. It's like a Java interface, but it's a little different, right? So Rust doesn't have this idea of true struct-based polymorphism, right? You can't have a struct called shape and then have a struct called circle, which inherits it directly, right? You need to have a higher level abstraction, like a trait, and maybe you could call that shape. In this case, I've called it has area because it's a little clearer with that language, right? With that English flow, that the trait is something. It's a trait. It's a characteristic of a particular struct, and then you can assign many different traits, right? So if I had something has perimeter, has circumference, I could also implement those for circle, right? In separate blocks. Right, so it's not 100% analogous to something like a polymorphic object-oriented language, but you can get pretty close, right? You can also do struct composition, right? So you could have structs within structs, and that's another way to realize something similar to object-oriented design, but not quite the same.
Right. Okay, thank you.
Yeah.
A question about return type.
Yeah.
It's interesting that all the functions are being set up with fn instead of some explicit type. So then I guess it's inferring based on what the expression is at the end. But if you were to replace a void function from C, where it's not actually returning anything, but it's just doing stuff, do you just not leave any expression?
Yeah, you just have no return type. So this is the return type after the arrow, right? The return type of this is a 64-bit float. If you didn't have that, you just have in parentheses, open bracket, right? There would be nothing.
Okay.
Yeah, good question. Okay, right. So there's a lot more details, and as you learn Rust, the basic stuff will become clear. Okay, so moving on. Some of the more cool things you can do is functional style patterns and matching, right? So you can have basic tuples; those are supported by Rust. You can do, here's a very simple example, right? We can define something to be, in this case, we define number to be the returned value, right? The result of this match statement, right? So it basically says, is, depending, it's like a switch statement sort of, but much more expressive, right? Depending on the value of X, we're going to match on different values of X. If it's 1, we return this. If it's 2, we return this. If it's 3, and if this condition, we return this, right? Or in all other cases, this is like the default case in a switch statement, we do something else, right? So this is a really simple match statement, but it can be very, very expressive, right? There's also the concept of scope, right? Rust is a scoped language, and it also allows you to do what's called shadowing, which is redefine a particular variable name within a scope, right? So here at the top, we have a 32-bit signed integer named X, give it the value 8. So when I print it within this scope, right, X still has the value 8, right? It's still bound to this object in memory, right? I can also re-scope it, which is called shadowing, right? And then for the remainder of this scope, right, the scope of X here, it will be this value. So X will be rebound to this object in memory, right, which is just a value on, a local stack variable, right? And then when I exit the scope, this X is still in scope, or it's back in scope rather. So here, when I continue on, I'll get 8 again, right? Then I can shadow it again. So this isn't super interesting. I just wanted to clarify it in case you do see something like this in your code or wonder, hey, why am I allowed to redefine something like this? Okay. So one of my personal favorite features of Rust is the way that it handles enums, right? So in this case, we have an enum called sum. And unlike C, where you can just have basically, a key value sort of thing, where you say this keyword foo is given a value 1, right? You can do that in Rust, but you can have typed enums in which each variant of the enum has a different type, right? So in this case, foo is a variant of the enum that just stands alone by itself, kind of like a C-style enum variant. It doesn't have anything within it per se, right? But bar does. It has 2 unnamed things like a tuple, and Baz itself has a struct within it, right? So this is super nice. And then when you integrate this with something like match statements, you can see how powerful it can be. And you can use this lovely Rust syntax to extract little bits of something in an enum and handle all of these cases, right? So here's a simple example. I'm creating a variant of this enum, and the variant is Baz, so it's of type Baz, right? And I'm giving it initial values. And then I'm basically saying, hey, let me get some value out of it. And then for each variant, again, sort of like a switch statement, I'm saying, here in the case of foo, let's default to 0. In the case of bar, let's get that first U size, right, up here. And then in the case of the Baz variant, let's get quite powerful, right? And there's various things like this is ignore this thing or ignore the rest of the things in the struct, right? And this allows you to very easily handle a bunch of different cases that you may see from various enums, right? So I really recommend using typed enums like this. You can put arbitrary things in here, structs, elements, whatever you want, right? It's super expressive. So another thing that Rust takes from functional programming languages is the idea of closures, right? Which is just another way of saying higher order functions, right? So here's a great example. Here I'm just giving the value of 5 to this variable num. And here I am defining a closure, right? And between the vertical bars is the arguments. This is kind of like the parameter list of a regular function. And then after this, optionally in curly braces, is the body of the function, right? And like I said, this is the last statement. Really, it's the only statement of this closure, but it's the last statement. So this is the return value of this function, right? Now, like I showed before, Rust lets you omit a lot of things, and it can infer, right, types everywhere, right? So in this case, it knows that the type of this closure, right, plus num it's a variable, but it's actually a function, right? It knows that the type of plus num is a function that accepts one argument of a 32-bit signed integer. And here, again, it's inferring that anything you add to this also needs to be a 32-bit integer. So it knows that it's returning a 32-bit integer, right? And I didn't have to declare any of that. I can if I want to, but I didn't have to, right? So then when I call it, it's going to basically know, it's going to realize that within its current scope, there was a value for a variable named num, and it's going to capture that such that when you call plus num and you pass in 7, 7 becomes x, so you get 7 plus 5 from this environment variable, right? That was captured into this closure, and then you get 12, right? So here's a slightly more complex example. You can also capture items mutably, right? So in this case, this is just a slightly more complex closure that takes no arguments, right? So 2 bars with nothing in between. And it has a larger function body, again, specified by these curly braces. And all it does is increment the value of this count variable, which it captured inside the closure, right? And then it prints it. So the first time I call this, right, you're going to get 4. And then the next time you call this, you're going to get 5. And what's unique here is, like every functional language, at the end of this count itself, if you were to just say print count here, it will be 5, right? Because this closure captured the value of this, environmental variable here, count, and it modified it. So that's the idea of higher order functions. There's a lot of complexity here, but those are some basics.
Kevin, this just look like C's macro, right? I can just define macro in C, just behave exactly like this.
You could, but you're not going to get this unique idea of capturing something from the surrounding scope, right? And I would also say that macros aren't, syntactically checked; they're just lexical in C. And you can pass these closures around as function arguments themselves, and all of that doesn't really work out in C, right? There's not like a C type that allows you to pass a function. You can pass a function pointer, but it's not quite the same thing.
I mean, can I pass a macro? No, I can't.
Maybe, but I mean, again, it's all lexical. It's not actually syntactically checked. So it's up to you just to get it right. And so you can think of a closure basically as a function plus the environment. So if you were to represent a closure by a struct, you would say, here's the items that I've captured. It's a list of the items I've captured, and then a list of the commands that I'm going to do on those items, right? It's basically a function plus some environment.
Right, you cannot use a closure outside the scope it is defined, right?
Right, yeah. So this basically needs to persist for as long as this closure is used, right? And I'll get into how Rust checks that when we talk about ownership and borrowing.
I think that's actually the unique strengths of Rust compared to, say, macro, because macro doesn't have this scope notion, right? It's just you can just expand.
Right. So I should also clarify. I think I mentioned it at the beginning, but I'll emphasize. Closures and capturing exist in many other languages, right? Functional languages, even in C++, you have them, right? Sometimes they're referred to as lambdas. You may have heard that terminology as well. And it's not like a Rust invention, right? This is just closures expressed in Rust syntax in terms that the compiler knows. Okay, so in the interest of time, I'll move on. Well, were there any other questions, I guess, on closures?
Can you have a closure with like a local variable? Like you define count the first time you call the closure, and then every time you run the closure, you increment the count that you created the first time you used it?
Yeah, so in this case, I'm capturing count from the enclosing scope. But yeah, I could have another local variable inside the closure that's local to just that invocation of the closure, like count2 equals 2 or something. And then that wouldn't have any impacts on the scope outside of the closure, just like a local function variable.
But I mean, like if you only want to initialize it once, like, is there any notion of like static local variables in Rust?
Static local variables? Oh, I mean, sure. Yeah. You could have a static. I could say that static. I could say that count would be static. So static in C has a different meaning than in other languages, right? Static in C just means private to a module. Perhaps you meant const. I'm not sure. In Rust and in other languages, static means it's not stack allocated. It's not heap allocated. It's embedded within the program's data section itself, the object file, right? So you don't allocate space for it on the heap or the stack. It's actually within the program's executable space. Right? That's what static means. So I'm not exactly sure what you meant by a static local
in
variable.
In C, there's two notions of static. If it's in like a global scope, then it's private to, then it means private basically.
Mhm.
The alternative notion
I
is
see,
if
I
it's
see. Yeah,
local.
yeah.
Okay.
You meant static in terms of like an object-oriented way, and that there's always a single instance of that particular thing, no matter how many times you call the function, right?
Right.
Yeah, you can do that, sure. Static is basically the same thing in Rust, right? As that. It's not exactly the same, but using static in Rust will get you that effect as well. Yeah.
Is that unsafe, Kevin?
Yeah, I don't want to get too complicated, but yes. If you want to modify a static variable in Rust directly, you need to use unsafe, or you need to use a wrapper type like a mutex or something that can guarantee thread safety. This is far, far, far more complicated than what we're getting now.
But
yes.
That could cause point deduction in their lab 3 because they need to minimize the use of unsafe features.
Sure. So when you first learn about Rust, you'll immediately see that if you have some kind of static or quote global variable, right? If you want it to modify it, it needs to be, if you have like static mute count equals 3 or something, right? If you want to modify that directly, you'll need to use unsafe code. And that's just because a static variable, right, can be accessed by any thread at any time, right? So if you want to avoid unsafe, you can use something like a mutex, right? Or an atomic type, which is thread safe and will atomically set the value of that static data item, right? A lot of detail. I'm happy to show examples of this after the talk if you want, or on Slack. Okay, anywho, so that's basically the idea of closures and captures. Just another quick example of imperative versus functional. So here I have just a very simple function that finds the sum of all of the squares that are odd, right, from 0 to 1,000, right? So this is how you might do it in like a standard C style imperative programming style, right? You just basically go, iterate over all the numbers, you're checking all these conditionals, right? And then you're, accumulating the values in some outside accumulator, right? And then you print. Pretty standard stuff. This is how you would do it in C. Rust also has these idea of a more functional blend, right? Where you have these methods that kind of operate on the previous thing they were sent, right? So in this case, I broke them each down into different lines, but these functions are super nice and they all work on this iterator type in Rust. Basically, the first line says, take all of the numbers from 0 up to infinity, right? For each one of those numbers, square it, right? And then I'm going to use this special take while operator to say, any of these numbers where the square is less than 1,000, I'll take that, right? So that limits the range here down from infinity. And then only choose the ones that are odd, right? And then fold them all into an initial value of 0, which is another way of saying sum them up, right? So this is a little bit of complexity, but this is kind of how you would do things in a more functional style approach, where you have a series of iterators and these combinatorial functions that each operate on the previous output of each other, right? So this is kind of, each one of these is a little function, right? A little closure, right? Yeah, so you don't need to understand all of this, but that's kind of another cool way of using functional syntax within Rust. And you can use both of those. You can mix and match these two different styles. Okay, right, so now let's get to the actual meat of Rust, the notion of ownership and borrowing, which in Rust is the key to ensuring memory safety at compile time. Okay, so what is ownership? Every value in Rust has a single owner, and that's statically known, meaning it's known at compile time, for all times, all points, and all code paths. And then the owned value will be implicitly and automatically dropped, which is basically Rust's term for freeing or destroying something, when that owned object falls out of scope, right? You can also have references to an owned value, right? And those have a limited duration. And of course, that duration is based on the lifetime of the owned value itself. So we refer to this as its lifetime. And it also, this is tracked at compile time. So references are like pointers. They're not quite the same thing. If you're familiar with references in C++, it is basically the same thing as that, but they have a clear, explicit lifetime. And I'll show examples of this. The great thing about Rust is it requires RAII, right, which is called resource acquisition is initialization, meaning that when you create a reference, you have to immediately assign it to, borrow or to refer to a particular owned value, right? So you can't create a dangling reference that points to nothing. In C, obviously, everything you can do that if you want with pointers, right? But this ensures that you're not able to ever create an invalid reference. Right? So here's some rules as to basically how that works, right? So through these rules about ownership and borrowing, again, enforced by the compiler, we have this property, right? And the property is that at any given point, for a single object, you can have aliasing of that object, or you can have mutation, but you can't have both at the same time, right? And I'll show an example of that in the future. All right. So for however long something is borrowed in terms of scope, right, lines of code, the owner of that object cannot free, move, or change the underlying value, right? So kind of borrowing is sort of an exclusive thing if it's mutable, or aliasing is non-exclusive but immutable borrow, so you can't change it. All right. So again, examples coming. But the benefits of this is that you don't need an underlying runtime because all of this can be checked by the compiler. Right? We get memory safety, and we're free from data races, even in the face of concurrency. Right? One prerequisite to this is that Rust needs to know what is mutable and what is immutable at compile time. Right? So by default, all Rust variables are immutable. I think I showed you that before. And then you use the keyword mute to declare something that is mutable. So here's a very simple example. You may say, okay, this looks good. I'm going to declare something called A. I'm going to add 1 to it and print it. And you may throw a fit and say, why is this a compiler error? It's simply because A is not mutable. Right? So in a simple case like this, you can just fix it and use the actual keyword mute. Right? And at this point, you've basically told Rust, hey, I want to explicitly declare this binding, this variable A, right, which refers to this value in memory, this 32-bit signed integer, as mutable, meaning that anyone who refers to it can then change its value, right? So this works. And you may be saying, oh, this is really stupid, but that explicitness is kind of the key of making sure that we don't have both aliasing and mutability at the same time. All right, so here's a very simple example of ownership. So here I have one vector. It's a 3-element vector. All right, so when I do this, so when I do that, basically I have a variable v on the stack, which points to a vector on the heap. Now here I'm assigning v to v2, right? Which is basically moving. I'm moving the contents of this, again, not in actual memory, just conceptually at the compile level, right? I'm moving it from v to v2, right? You can think of it as renaming or transferring ownership, right? So at this point, when I try to use the original v, I cannot do that. I get an error that says I've used this moved value, right? Now this may confuse you a lot, but again, this is about ensuring aliasing XOR mutability, right? If we had two aliases, right, two names that were bound to the same vector, and maybe one of them was mutable, Rust wouldn't know at compile time which one you wanted to mutate and which one perhaps you sent to another thread in an immutable way that you were reading, and that could cause a data race, right? So if we did something like this, it would violate Rust's memory safety guarantees. And you may say, this is so stupid. Obviously, I know in a single threaded case here, nothing is going to go wrong. And you're right, right? But keep in mind, I could ship this off to another thread. I could take V1, or I could take V and V2 and move it and do whatever I want with it. The point is, if Rust prevents this ahead of time, right, initially by basically rendering V no longer usable, then it can be guaranteed that whatever I do with V2 at this point will be valid and safe. So ownership is also, as I was alluding to, it also is moved or transferred across functions, right? So in this case, I have the same vector I've allocated, and then I'm moving it to this function, right? So this takes V as an owned value, which sometimes we also call consuming v, right? And here we can do anything with v because we own it, right? It's not a reference, it's a direct owned type. And then here, down here, if we try to actually use v, we get the same problem, right? We've already moved it to this function, right? So I think this, also shows how clear ownership is, right? So in this case, the function do anything, more specifically, its scope is said to own v, right? What that means is that the Rust compiler knows that when this scope ends, since v is owned, it's totally safe for v to be dropped and subsequently freed and deallocated from the heap once the scope of this function ends, right? So that's basically how memory management works, right? Here I allocated this heap, this vector on the heap, and then here, since I've moved the ownership, I've transferred the ownership to the do anything function, I know that it's safe for me to free it, because at this point, nothing here can use v anymore, right? So if we try to build this, we'd get a compiler error here when we try to print v, because the ownership has been moved. And that's right. That's the proper way to do things, because at this point, the memory that v refers to could have been reused for something, since it will have been freed. So any questions here?
Can you like return, if you return v from that function, like is that sort of method of like giving ownership back to the top level code? Okay.
You're reading my mind. That's exactly the next the next slide.
Gotcha. Okay. Thanks.
Yeah. So that is one way to kind of solve the problem of, maybe you want to continue to use something that you pass to another function, right? Yeah, you can do that, right? So here I have two vectors. Maybe I want to calculate the sum of all the elements in both vectors. I didn't do that here, right? But, I can return those things that I passed by ownership back to the caller, right? So here I do that when I call foo, and I'm getting v1, v2, and an additional thing that this function created, just a primitive value here, back from that function. And then here I can use v1 and v2 again. But semantically, they're not actually the same, right? v1 doesn't refer to this, even though it was reassigned. But here I could have returned v2, then v1, and then they would have been flipped here. I didn't, because that's confusing as hell, but I could have done that. What I'm doing here is I'm creating new bindings for v1 and v2 that refer to the vectors that were returned by this function, right? So yes, this is one way to get around the issue of ownership. Basically return all of the things that you transferred out to that function such that you can retake ownership of them in the caller, right? That's fine. For many functions, that's totally fine. Maybe, that's kind of like a more pure design, right? In the sense of side effects, right? You don't have any side effects. Everything that the function does is returned. So that's purely functional, right? But it's a little bit tedious, right? What if I was passing 50 things into this function? Do I want to return 50 things? Maybe not. So that's where borrowing comes into play, all right? So Rust allows you to borrow something either mutably or immutably, right? So here I've defined two variables, right? X and Y, they have the values 3 and 5. And in this case, note that I'm not accepting in the function signature, I'm not accepting an owned value, I'm accepting a borrowed reference to an owned value. And here I'm accepting a mutable borrowed reference to an owned value, right? So in this function, I am allowed to read the value of A. I am allowed to read and write the value of B, but I don't own them. So I can't transfer them out to another function if I call that within foo. And because I don't own them, they're not dropped, right? So Rust won't insert a call to the drop, the destructor here for these values. In the case of an integer, you don't do anything, but if it was a string or a heap allocated value, it would deallocate it, right? So, and then in order to make sure that this syntax works, I need to express that I'm not passing in X directly. I'm borrowing X, which I use the ampersand syntax for. And here I'm borrowing Y in a mutable fashion, which I use ampersand mute for, right? And at this point, the caller, the main function, still owns X and Y. So I can use them as normal, right? So this is kind of a very common syntax and a very common function structure that you'll see. And it's a great way to limit access, right? Or gate access to what a function can and can't do, right? Just at compile time, I can be guaranteed that A will be immutable, B will be mutable, and X and Y will last and persist throughout the invocation of foo, right? So I think that also kind of clarifies, I think Will had a question about, syntax. This doesn't return anything, right? But it has the side effects potentially of modifying B. Right? Okay. So a couple of more details. I think I've already mentioned this, right? But just to reemphasize, when an object that is owned falls out of scope, the compiler auto inserts a call to its type-specific invocation of drop, right? And for each type that you defined, you can actually customize what the action of drop does, right? So for the case of a string or something, you would deallocate all of the memory that backs those characters on the heap, right? Something more interesting, like let's say you had a mutex, right? When you actually reach the end of the scope, so here I've locked the mutex and I'm modifying it, right? When I reach the end of this scope that I've defined here, the lock itself falls out of scope and it's dropped. So this is realized to be a guard type, which you can read about, and that's returned when you call lock. But basically what it does is ensure that no matter what you do, when when you've acquired the lock on a mutex, once it falls out of scope, no matter who you send it to, who you pass it to, right, it will always get unlocked automatically, right? So that prevents you from having to remember as a programmer to explicitly unlock it after you're done accessing it or something like that. So that's super convenient. And we see that pattern a lot in Rust. And again, this is only possible due to ownership, right? In this case, lock string owns this mutex guard, which has an implicit reference back to the data in this mutex. And then we can modify it, right? We can like push, the string world onto the end of hello. And then once the scope is exited, the lock is automatically released. And therefore we wouldn't be able to access the inner data of the mutex without, again, locking it. And then finally, we have the actual mutex and the string object itself, which was declared to be a local variable within this function. So once the function ends, m itself is dropped, which means all of the internal items in that mutex structure are dropped, which means the string is dropped, and there it's deallocated from the heap, right? So I think that's kind of a cool example of what you can do with scope-based ownership and automatic dropping at Rust. It really makes resource management super convenient. Any questions here?
I got one 2 slides back.
Okay. Go ahead.
If foo, instead of returning the same types as what it was given in the first place, if it instead of returned like 3 bools, for instance, are we redefining in main? Are we redefining v1, v2 to be booleans? Like there's no, it has nothing to do with what it originally was. We're essentially defining it from scratch.
That's exactly right. You're re-scoping the names of v1 and v2. Yeah.
Okay, thanks.
Yeah, but of course, because it's strongly typed, you wouldn't be able to use you wouldn't be able to use them as vectors, right? You would only be able to use them as bools. And it would be the same thing as if you just wrote let v1 equals false here. Cool. Okay.
Yeah.
Great.
Thanks.
Yeah. Right. So, okay. So there are a lot of finer details of borrowing, which you'll get acquainted with really quick when you start digging into Rust. But just to highlight some of the top level rules, you can't obtain or borrow a mutable reference from an immutable object, right? And you also cannot mutate an object that was borrowed immutably. That makes sense, right? You can't violate the rules of mutability. Second point, you can't borrow more than one mutable reference at a time. And that guarantees atomicity, which is important even for a single thread, but super important for multiple threads to prevent data races. However, you can borrow something immutably many times, right? So that's aliasing XOR mutability, again, coming back to haunt you or coming back to help you, depending on your viewpoint. Another way of rephrasing that is you can't have simultaneous mutable and immutable references to the same own value. So this is exclusivity. Exclusivity. Sorry, can't say that word. Right. So another thing is, and probably the most important point, is when you borrow something, that lifetime of that reference type, right, ampersand X or whatever it is, has to end before the lifetime of the owned object that it refers back to ends. And this is basically Rust's way of preventing dangling references. So here's a clear example of that. Well, okay. First, just let me compare this to C++, then I'll give you a clear example of that. So in C++, right, we have both pointer types and reference types. Rust does have pointer types, but they're unsafe. So in this case, right, we have a non-constant pointer, a mutable pointer to a non-constant mutable value. Here we have a non-constant pointer to a const value, right? So a mutable pointer to an immutable value, right? And then all these different variations, right? They're very confusing and pretty difficult to read, right? C++ also has reference types, right? So here, again, it's implicit that it's mutable rather than explicit that it's mutable in Rust, right? And then you can combine all these as well, right? So in Rust, it's a lot simpler, right? Here you have a mutable value, and then you assign it, right? Here you have y, which is a mutable reference to x. And then here you have a mutable reference to a mutable value, right? So you could reassign y here, right? To refer to another thing that you wanted to mutate, right? This is not super common. You'll typically see this, and then you'll just say, y equals 5. And it works just like a reference should. So it's sort of the inverse approach to C++, right? Whereas in C++, the idea of something being constant has to be explicitly stated. In Rust, the idea of something being mutable has to be explicitly stated. So again, just a slight difference there. Okay, so now here's a simple example of lifetimes, right? So here I have a very simple main function. All I'm doing is printing two things. I'm printing the value of y and the value of a reference that I get, right? When I call the bad reference function, what I would like to do here is define a local variable x, and I want to return a reference to this, right? Which I express with this syntax. Now, what's the problem with this, right? We don't know how long should this x value last. Ideally, it should last until the caller is done using it. But how do we know how long the caller will use it? We don't, right? I could pass it to an arbitrary function, which could do anything with it, right? So there's no way, because this is a local variable that will be destroyed after this function scope ends, there's no way for me to express to the Rust compiler that I want this variable x, this reference, to last as long as, quote, it needs to, right? You don't know. In C, you could do this because it's up to you to make sure that this thing lasts as long as you need it to, right? But that's not safe. So what's the right way to do this? With lifetimes, right? So I'm going to introduce a little bit of new syntax here. And the syntax is this tick and then a character, right? Or one or more characters, tick and then an identifier, right? So what this means, this is a lifetime, right? So you typically see them only on references, right? Own values don't have a lifetime, an explicit lifetime. They just last for however long they're in scope, right? But references do have an explicit lifetime. So anytime you have some kind of return type, right? You'll need to specify the lifetime of that reference, only if it's a borrowed value. But let me take you through what this function does. So first I'm creating a string, which is heap allocated, but that doesn't really matter. And then I'm obtaining a reference to the part of it that is name, right? Which is the third through the 6th or 7th exclusive character, right? And this is one way to do that, right? So this is called a slice. This is an index, right? I'm taking this range of the string. And what I've done is basically when I call good reference here, I'm saying that the lifetime of this borrowed string slice, which is again a reference to the string, needs to have the same lifetime as whatever was passed in, right? So I'm parameterizing this function with the lifetime, and I've given it the name s. Again, you could put anything here. I could call it my string lifetime. It just needs to be the same thing here and here, right? And this is a very clear way to specify at compile time, again, at compile time, that whatever I return from this function needs to last exactly as long as whatever I passed in, right? So here, big string, what I passed in was y, right? I passed in a reference to y. So this reference, yref, can only last at the maximum as long as the lifetime of this value y, right? So here I'm borrowing yref is a borrowed reference to something, a string y, again, which is owned on the heap, right? And it has the type of a string reference, right? And it has the lifetime s. So if I were to do something like move y, like maybe perhaps I want to send it to another function, or I want to clean it up and explicitly destroy it, I need to make sure that I don't use yref after I've done that, right? Otherwise, that would be a dangling reference, right? So this is how you do that. This is the syntax required to specify what a lifetime means, where it comes from, and also, where it goes to or what it's returned as. So lifetimes are probably the most complicated part of Rust, but I just wanted to give you a clear example of how they work in the case of referencing parts of a string.
Kevin, I have a question here. For the bracket here, the tick s, is that indicate that's just a variable?
This right here?
Right.
Yes, this is a type parameter to the function.
All right.
Right. Yeah, so this is basically saying, you could give this any name. It's basically saying, I know that this function needs at least one name, and that name needs to be used as a lifetime, right? So you could also have multiple lifetimes if you have multiple arguments with different lifetimes. You can have multiple parameters here.
When you define that function, you have explicitly say this function require you specify a lifetime as the input.
So the first, that's a good question. So the first compile error, if we were to try to build this bad reference function, is it's going to say, hey, I need you to tell me the lifetime of this because I don't know how long it should last, right? And that's a huge advantage over C++, right? In C++, this would be legal because it's on you to make sure that the reference lasts as long as whatever it's referring to, right? But Rust says, that's horribly unsafe. It's complicated. I'm going to make you explicitly tell me how long this should last. And this is how you do it. You say the return type must last. It has the same lifetime, must last as long as whatever the input parameter was.
I mean, it's you do it, you developer do it, right? You put this into the type of the function.
That's correct, right? Yeah, and right. So there are ways that you can generally omit it, but for a simple standalone function like this, you do need to explicitly state what it comes from, right? And in any case, I'm doing it as a kind of an academic exercise, just so you can see how you might tell this function, or specifically the Rust compiler, how long this return type should last.
Okay.
Right.
So I think. Okay, go ahead, Kevin.
Oh yeah, I was just going to say the key point here, and this is pretty much my last slide. The key point here is that there is no way to abuse this. You cannot, at least in safe code, you cannot say, hey, I want to extend this lifetime, pass it over to something else, and have Rust allow you to build that. It will throw a compile error if you try to use this beyond the lifetime of this original string. Okay. Yeah, is the class over or something?
I think we're right on time.
Okay, yeah. So I just wanted to quickly show an example and see, right? The same kind of thing, right? Here I'm returning a reference, in this case it's a pointer because it's C, to a local stack variable in, right? So the problem with this is, again, dangling pointers. We don't know what NP will point to after this function returns because its stack space will be reused, right? And we don't know what will happen if we try to dereference that pointer. Right, so that's a major problem. So in my opinion, this is the #1 strength of Rust, giving explicit lifetimes to especially return values from a function and defining those lifetimes in terms of something else that you passed into the function. You're right, so just real quick, this is the last technical slide. Doing something like ownership and borrow checking allows you to have safe concurrency in the presence of multiple threads, right? So here what I've done is I have allocated space for this dummy struct on the heap. That's what box is. It's just a container for something on the heap. I define it to be mutable, which means I can capture it within a closure, right? So this is a closure, and this is how you spawn a thread. You just say, run this function, this closure in another thread. I can capture it mutably, right? And then I am able to increment the value in a different thread. But here I've also tried to capture it mutably. I've tried to reference it and increment it here. Now in C and C++, you can totally do this, no problem, right? You can borrow something mutably and then borrow it again mutably, but not in Rust, right? Because again, obviously this is a clear data race. Depending on how these two threads are interleaved, your main thread and this other thread, you could end up with a value of 1, 2, maybe anything, but probably just 1 and 2. Right, so that's how we get safe concurrency at compile time through memory safety by limiting the number of simultaneous mutable borrows we can have. Okay, so that's pretty much it. Just in summary, Rust kind of defies the tradition or the convention that you either need to have a lot of control over something with no safety, or you need to have no control with a lot of safety, right? Rust gives you both at compile time. All right, so now I'll take any questions. There's quite a lot of other topics to cover, things like higher level abstractions, generics, traits, which I briefly touched on, but they're very detailed. But I would recommend starting your reading with the Rust book. It's online and free, and it's a really good resource. It'll only take you maybe a couple of hours to go through, and it clarifies all of these points in more depth. Okay, that's all I've got. I'm around, I'm free for the next little while, so I can answer questions or give demos. Thanks.
Thank you, Kevin. All right, any questions?
I got one about
Hi.
lifetimes. Oh, sorry.
Oh,
Rishan, you.
okay. I have a question about the unsafe Rust. I mean,
Yeah.
Given my impression that Rust can guarantee safety only if you play by the rules. If you use unsafe Rust, you don't get all those security guarantees, right? So, if you are a hostile programmer, you want to do some hacking, and you use unsafe Rust, I mean, there's no way for the compiler or any way you can be stopped, right?
Yeah, so first of all, I think you're conflating a couple different things. You're conflating the idea of an operating system protecting multiple different processes from each other, right? Or multiple different users, which happens regardless of language, right? In this case, like, yeah, you're a programmer, you're developing something that's unsafe. I mean, in a standard OS, the worst you can do is shoot yourself in the foot, right? Unsafe is basically just a way to say, hey, compiler, I know what I'm doing. Trust me on this one, right? I know that I'm doing it right. It's only really used to express something that the compiler can't check, right? And in the case of an embedded system, you will need to use unsafe, right? So here's another example.
Yep.
In the case of inline assembly, right? You may need to, in this case, this is writing something to an x86 port, and you need to use the out-L assembly instruction, right? So this has to be unsafe because Rust doesn't know the semantics of every assembly instruction, right? The idea is that unsafe is gated, right? There's a specific block, and only that block, right? Only stuff that is within that unsafe block can use unsafe code, functions, and syntax, right? So for example, if you had some weird memory error cropping up, you could safely ignore 99% of the program and only search for your unsafe blocks, and then make sure that what you're doing in those unsafe blocks is sound, right? So that's the huge advantage of kind of opt-out safety. Everything's safe by default, and then if you want to opt out from it, you have to explicitly say, hey, this region is unsafe. Does that answer your question?
I guess, yeah. So suppose I'm building an operating system with Rust, and some users will build some hostile programs, try to steal some information from the kernel. Do I still need to do all those security protection inside my kernel to stop the hostile users? Or
sure. I mean, yeah, it totally
make
depends
makes
on
things easier?
Yeah, it totally depends on the design of your system, right? In a traditional system, where you have user space and kernel space, you'd have system calls, right? And you'd want to check that everything that you get from user space is, valid, like valid pointers, the buffers exist, things like that, before you actually then move over to safe Rust code in your kernel, right? Or if you wanted to just limit your users to using only safe Rust code in their applications, right? Then you wouldn't need to have that extra protection and checks in there, right? Because the compiler would already be limiting. So this is kind of, beyond the concept of just Rust. But the idea is when you implement something unsafe, you want to wrap it in a safe abstraction, right? That performs all of these checks, whatever checks are necessary before you enter that unsafe block, right? So here, there's not really any checks necessary. But, let's say that you were doing something like, context switching or writing to some arbitrary region of memory, right? First, you need to check that that memory region exists, that it's valid, that nobody else is accessing it, and then you can proceed with the unsafe code. It really just depends on what's happening in that unsafe block. And that's going to determine what checks you need to have in order to bridge the safe and the unsafe world, right?
Okay.
So I should clarify, at the lowest level, everything is unsafe, right? All of Rust safety is based on a series of checks, right? A series of invariants that guarantee whatever the underlying unsafe code is doing won't break your assumptions, AKA it's sound, right? So the whole notion of safety is basically just, it's informing the caller that, hey, within this, we already ensure that all of the guarantees we've exposed to you are checked and enforced. So if you implement unsafe code, it's on you to enforce those guarantees rather than the compiler.
Okay, I see. Thank you.
Got it? Okay. Sure. Did you have a question, Will? I think I heard you.
Yeah, one about lifetimes. Once
Yeah.
you set the lifetime, like at the creation of the variable, let's say you set it to 4. I think of it almost like the TTL in networks, where ordinarily you'd be decrementing it 1 every time. But imaginably there could be some circumstance where you want to like decrease by 2 or more. Is there some way to change how much time, not really time, but you know what I mean, like how much longer it can last?
Yeah, lifetimes don't really have that notion of time, right? So it is time in terms of like program execution flow, but it's actually scope, right? So you could maybe call it life scopes or scoped ranges or something, right? It's solely based on scope, right? So to say that, maybe in this example, I want to like allow this particular returned reference to the string that was inputted, right, to big string, right, to only exist for like 3 more statements or something. You can't do that, right? What you could do is surround this statement, right, in another scope and enclosing curly braces, right? And then when yref falls out of scope, right, nobody can access it. So therefore you've effectively limited the lifetime of that borrowed reference to just that scope. Right? I haven't done that here, but I mean, effectively I have, because the functions are also, gated in these curly braces. But it's not like a numeric or like a time in that sense. It's purely based on scope.
That makes more sense. Thanks.
Yeah, I think that as you actually play with lifetimes, this is honestly, I wish that I would have seen this example when I was first learning lifetimes. This is mostly how you'll see them. It's super convenient. Now you can also have lifetimes in structs, right? So if you want to have a reference as a struct field, you also need to specify the lifetime of that reference within the struct. So you'll see this, like you can have, struct, my struct, and then the same kind of lifetime parameter here. And then in the field, you have a similar one. I mean, I can just show it, but yeah, I mean, I think you get the idea of it. If you want me to show, I'm happy to give an example.
All right. Okay. I think we're kind of way over time, but I think I have 2 suggestions for all of you, since you're learning Rust and also working on lab 3, right? For lab 2 and lab 3, you are using stack. All your variables are actually put on stack, right? Think about when you use Rust and how the Rust guarantee you wouldn't have problem with the stack. Okay, that's number 1. Number 2 is involve the optional reading for your phone. I have, it's called the wall in memory, right? Talk about all the memory box caused by the use of C and C++. If you have time, go through that article and see any of the problems will be gone if you just use Rust, right? Basically, my opinion is if everybody uses safe Rust, the world would be much better place, right? You wouldn't have the eternal wall in memory like that article talked about. Okay.
Okay, yeah, so I can stick around if anybody has additional questions. Are there other questions or things? I mean, maybe I can do another meetup session or something once you guys actually get into Rust more and you want more demos or something. Just let me know. Okay, anything else? Okay, yeah, thanks, no problem, happy to do it. Okay, great.
We'll see you guys next Monday, right? This Wednesday we don't have a class, right? Is my understanding? Okay, good. We're starting working on lab 3, learning Rust. I'll see you next week.
Good luck. See you guys.
All right, thank you, Kevin.
No problem.
Thank you.